Okay, so this lecture today is sort of based on problem set 6, but it's about the critical exponents in the van der Waals gas. Okay, and so we had actually worked out we had derived the free energy that gave the van der Waals equation of state, which had the following form. And as a bonus, we were able to identify A and B with some microscopic quantities in some, we had done a virial expansion, if you remember. Okay. And so the first item is to identify the critical point, identify the critical point, that is the value of PVT, where there is an inflection point. Okay, so this will define, and those critical values we'll call PC, VC, and TC. We want to determine those values. And so the simple way is to just go ahead and take derivatives of this equation. So let's just take derivation of this equation. So we get dP by dV minus 2an square upon v cubed into v minus b plus b minus b plus an square. I'm just doing Leibniz rule into 1, and derivative of this thing equal to 0. So this is equation A. Now to get the second derivative, just take a second derivative of A with respect to B, and we get this equation, which is this is what we get. Okay, so now we just have to set dP and dV equal to 0 and set V equal to Vc. There's no T in this, but that we'll get from the van der Waals equation of state once we determine PC and TC. Okay, so let's look at B. In B, set V equal to Vc, V equal to PC, and of course dP by dV then becomes 0, and d square P by dV square equal to 0. So if you look at this, okay, so d square P by this thing is 0 plus minus, so this dP by dV is 0, so I get minus 4a n square by v cubed, vc cubed equal to 0, and this is power 4. Okay, so we can remove some pull out factors like a by vc cubed we can remove completely, even n square we can remove, so we get 6 by vc Okay, you can simplify this, and this implies VC is 3B, I guess. Okay, so now we go to A.
Sir, it's supposed to be 3 and B.
3 and B, correct. That's because I consistently forgot to put N's here and nobody objected. I think even here. Thank you. Okay, so now in what we will do is go back to A and set VC equal to 3 and B, and of course dP by dV should be 0. If we do this, so you look here, this term goes to 0, and this just becomes 2NB, and this will be some. So let's write those things out. Okay, so we get write those things out and then take it from there. Okay, so A by 27B cubed into 2B plus PC plus A by 9B square equal to 0. And if you simplify this, okay, so now we need to determine TC. Okay, so once you do that thing, you get KBTC. Okay, so this is what you get. So for these values, so yeah, and I forgot, I put KB equal to 1, so please, I'll correct the problem set also. This says KBTC equal to this thing, okay? Sorry about that. Okay, so what is an inflection point? I mean, so what happens is that, so at an inflection point, the second derivative change sign, okay, the curvature of a curve changes sign. Okay, so if you have something which goes like this and it's going to do something like this, so this would be like the point of inflection. Okay, so this is curvature is this way and this is this way. Okay, so that's what an inflection point is, and so you guys, so here in this case, so once you get, if you look at the curve, so this would be for say t equal to tc, you will find the inflection point, and that is defined to be the critical. Okay, so useful change of variables is to just say that, p lowercase p is capital P by PC. Similarly, upper small lowercase v is capital.
Sir?
Yeah.
If it were a straight line also, the second derivative will be 0. So
Yeah, I mean, but in a straight line, everything, it doesn't, I mean, it is zero everywhere. It has zero curvature everywhere. There is no inflection, no single inflection point. I mean, there is like so, I mean, it's not this kind of picture, like the picture I drew. Okay. By this definition, every point will be, but in a straight line, so the point is straight line will not satisfy, so we put two conditions. We said second derivative should be zero, but we also said first derivative should be zero. Okay.
okay.
But even then you can have a horizontal line. Okay. So what I'm saying is that that's not what one means. Okay. Good question. Okay. So you define these things so that you get these variables. And yeah. So the second part is so the idea is we want to derive the exponents. Okay, critical exponents. Okay, so the analogy should be with magnetic systems. Okay, is the following. So a magnetization should go with V. Okay, and then what else? Magnetic field will go with P, pressure, and temperature will go with temperature. Okay, so exercise check that the exponents alpha, beta, gamma, delta that we define here are consistent with this identification. It's very easy. Just have to sit with the definitions. Okay. So what we're going to do now is first target is the critical exponent alpha. Okay, and so that is the specific heat at constant V goes as T minus Tc power alpha, or in reduced variables T minus 1 power alpha. Okay, so in the assignment you're asked to do it as a two-step. So we first compute S and then C. Okay, so let us do that. So then we just realize that df equal to minus SDT minus PdV
minus 5 dB plus
mu
mu
dm, right? So S is this partial derivative with respect to t, keeping V and N constant. Okay, so we have the expression for the free energy, which just let me write it for once. Okay. So plus half minus one more term, which is n square a upon b. Okay, so we just have to look at where are the dependence on t. There's one t coming here and there's one t coming here. That's it. Okay, so let's just do that. So we need to compute df by dt. Okay, so it is minus nkb into the object in the square brackets, and that is by taking this derivative. And of course, this is independent of v of t, so this term doesn't contribute. And then now we have to do 3 half log t. So if you do that, you'll get minus nkbt into 3 half. Okay, which is a constant. Is this okay? So this is what we get. And yeah, yes. So S by N is is there a sign problem? Minus, no, perfect. Plus KB times the square bracket, which I need the terms. It's okay. So what I'm going to do is be a little bit cavalier now, in the sense that I will not worry about constants. Okay, and I'll start writing terms. Okay, you will see why I did this. Okay, so out here, yeah. So this term v minus nb by this thing, I will just rewrite it as log of 3v minus 1. Okay, up to some constants, and that's a 3 half log t. I'll write it as t power 3 by 2 plus constant.
Sir, you put nkbt and 3 by 2 t term in the previous equation, and the next one it shows up as 3 by 2 kbt again.
That is this term, right?
Yes, sir.
Is this okay?
On the t and
T cancels out, right? Like from.
Oh yeah. It's a constant. Thanks. Oh god. Okay. So this is also a constant. So we need actually. Let me leave that constant just for the heck of it. Okay. So these are constants, but we can see that the key objects here is just kb log 3v minus 1 t power 3 half plus a constant. Why is it? That is because we want to compute cv, and cv is just what is cv? So little cv will be c by n. So let's write this little cv itself. Okay, so that will be t d little s by dt. But this is also the same as, you can prove this. Okay, so the operative thing is just 3 half log t. So it will be kb 3/2 kb. That's what you will get. Log t will give 1 by t times t is 1. So this is a constant. Just 3/2 kb per particle. And so this just says, and Cv is supposed to be t minus 1 power alpha. It's going to a constant. So this implies alpha is equal to 0. Okay. This also was similar to what happened in the case of the magnetic story, where it went to a constant. Again, we got alpha equal to 0. Okay, so that's this thing. So the next exponent we are going to compute is delta, not beta and gamma. We will do them later. So now we will do. So we can. So as a first, how is this defined? The definition is in terms of kappa t, which goes like minus v dp by t. That's the definition, keeping other things constant. Okay, so this is what we want to compute. And so what we will do is we will compute it not. So in our setup, we'll use little v. Again, easy to see that these two expressions I wrote are equal. Okay, so what we want is to compute. So first thing is easy one. Easy part is writing VDW equation in terms of reduced variables. Basically, the a and b will disappear, and you will get p of little p of v and t is equal to okay. So here in these reduced variables, the critical values is p equal to 1, little p equal to 1, little v equal to 1, and little t equal to 1. Okay. So what we want to ask is as t tends to 1 or capital T tends to Tc, okay, P not P kappa, goes as T minus 1 power delta. No, what is it we want to say here? T minus 1 power minus gamma. Okay, so we need to show this. So we have to take so first step is to take a derivative of this equation. So it implies so this is what we have, and we have multiplied by v. So v minus v did I mess up a sign here? Yeah, I did. Okay, so just go ahead and just let us set. We should just set t equal to 1. Oh no! I made a mistake. What is it I want to do? I want to do dv by dp, right? So this is not what I want. Sorry.
You just have to invert it. Then.
Yeah, I have to. I don't want to invert. I'll just do this. Okay, so I have to take. We'll say 1 equal to Okay, let's just do that. Okay, don't bother. Plus 6 over v cubed dv by dp. Okay, so instead of inverting, we just do it properly. That's all. Okay, minus 24 t 3v minus 1 whole square dv by dt. Okay, so this is what we have. Yeah, actually I could have inverted, but sorry, not being very smart here. Okay, so kappa definition is, this is wrong. I think even last lecture, few lectures back, I wrote it like this. Well, at least I'm consistent in my errors. Okay, so we just have to go ahead and solve for. Now we just solve for dv by dt. So to simplify this, we'll get. Okay, so now we just, all we have to do is to set v equal to 1 in this expression and see how it goes.
Sir, the 1 by v.
Okay, yeah, thanks. Okay,
Sir, minus sign also.
I think I've taken care of this one. Oh, I have to. Okay, but we just want to get the exponent, so for that viewpoint, so we get gamma equal to minus 1. Okay, so this is a critical exponent gamma. So now we will do delta. Again, if you remember, this was we got alpha gamma equal to 1 even in the magnetism. Okay, what it says is that this is on the critical isotherm. That is, you should set t equal to 1. Okay, what we find is that p minus 1, p goes, little p goes to 1, right? Goes as v minus 1 over delta. This is the definition of delta. Okay, so it's a bit of a mess, but we can do it. So what we get is p minus 1 equal to minus 3 by v square plus 8 t, put t equal to 1 divided by 3v minus 1. Okay, and this should be minus 1. Okay, but this minus 1, what we will do is we will write it as plus 3 minus 4. Okay, so you take these two guys and you simplify, you subtract this. Okay, sorry, I'll have to jump some steps, but simplest to do it in Mathematica. I don't have access to Mathematica, so I did it by hand this morning. Okay, so but this, if you check, goes to 0 again. So we have to extract this power of this thing, and so this goes like -3. Okay, so you can see at so this implies p minus 1 goes as v minus 1 whole cubed as v tends to 1, because these two guys are constant. So you can put 3v equal to 1 here in these things. So you'll get some factors. So what does that mean? Delta is 3. Okay, so that's what we get. Is this clear? Are there any questions? I've been just chugging along doing stuff. Okay.
So for the previous exponent gamma, in the definition, we also need b equal to it, right?
We
Was
need
not
to.
a problem,
We
right?
need
So
to. We need what?
in the end, you put small v equal to 1.
Yeah, we need that. We need that. Yeah, good point. Okay, so we need to do the last exponent. So let's do that. Which is exponent now? Beta, right? We need to determine beta. Okay, so this is not an easy one. Okay, and it's defined to be as follows. So Vg minus Vl. So there are two phases. This goes like Tc minus T power beta, or this is 1 minus little t or power beta. So we need to show that beta is something. Okay, so for first step is so this is a long step. So that's why this problem set is needed. So multiple steps are needed. So step 1 is to determine chemical potential as a function of V and T. But this is easy. What do? We just do dF by dN. We know F, so we can take a derivative. Okay, and express it in terms of reduced variables. And I think there might be KVs missing, but this is easy part. Okay, easy. Just taking a derivative and putting these things. And then what you will get is mu of V and little t. This goes like, I'm just copying the expression which I had. There might be a KB missing. I don't think that is important. Plus a function of t, which you are neglecting. Okay, you will see in a moment why. Okay, so the whole point here is that is when we so if you want to identify this, so the Gibbs potential, which we discussed last class, is actually G would be n times mu. G is a function of P, T, and N, and because of extensivity, that will be N times mu, which should be a function of P and T. Okay, but what we have here is mu as a function of P. So what we should write really is, we need to do some solution solving. Express V as a function of P and little t. Okay, only then. Okay, so and we know that when there are multi-phases on the coexistence curve, there are two phases coexisting, and we know that V of P can take many different values. Okay, so this is the most important point here, that we need to choose the correct values. Okay, so this is the key. So remember that there are multiple solutions to be given. Okay, and this is at the coexistence curve. Okay, so but if they are coexisting, mu L should be equal to mu G. This is one condition, and the pressure should be equal. These are the two conditions. So we get some ugly equations, and so the equations are ugly in the sense they are complicated. So this is, I think, PL equal to PG, I guess, 3 by VL square. So here I mean by VL, what I mean is the solution to the liquid phase, the value of V which corresponds to the liquid phase. Okay. And okay, I won't write the rest of the terms. It's the same terms on the left where you replace VL by VG. So this is the equality that we would like. Okay. So now the point is that what is it we should do? So we should solve for this, but we want to be close. So we want the values of pressure, etc., when it is very, very close to this thing. So the assumption. So we'll assume we just make this assumption that VL goes like 1 minus epsilon by 2, and Vg goes like 1 plus epsilon by 2, where epsilon is some parameter plus this just this thing, and so that we can now solve for. So you go here and plug it into these equations, and then work out what we. So we want to use these equations to solve for VL and VG. Okay, and we are looking for it very, very close to where the critical value. So we just assuming that VL is 1 minus and 1. Okay, so just in that neighborhood, we want to do this. So you just go ahead and you have to solve. Okay, so we have two equations and two unknowns, but it's not linear equations, so I think it's pretty complicated. So what you do is you plug this in and only work to first order in alpha, in epsilon, and then you work out what it is. So what you will see is Vg. So you need to just solve for epsilon, and in principle I should have put A and B here, but I think equal works. So where A and B are some constants which will this thing, we'll get VL minus Vg, or Vg minus VL is epsilon, and we have to solve for this epsilon, and that I won't do, but you can check that epsilon is 4 into 1 minus t power half. Oh, okay. So actually you needed to solve this to third order apparently. Now I also forgot it. So this you can't do by hand, and but you can do it in this thing. I would have shown it to you, except I don't have access to Mathematica where I'm right now. And so this just tells you that the exponent. So this is okay. We need to do this. So there will be lots of cancellations happening, and then so this will tell you that beta equal to half. Okay. So that's the thing. So the conclusion is that all exponents are the same as the mean field solution. Okay, so but our gases are in the are in 3 dimensions, and mean field did not work in the context of Ising model. It doesn't even work here. So the correct statement is that real gases of this type are in the same universality class as the 3D Ising model. Okay, and the 3D Ising model has alpha equal to 0.1, beta equal to 0.33. It's all numerically computed. Okay, so there are no precise something. So 1.24 and delta equal to some 4.79. So this is from simulations. Okay. By the way, it's an art to estimate these exponents in the on a computer, because your computer is by definition a finite system, and I told you that you will not be able to observe phase transitions in finite systems, and so I leave it as a puzzle as to how people get around that problem. Okay. So remember, we did some scaling. So some scaling is used, and they'll show some collapse. And there's also critical slowing which happens in the simulations as you get closer to the critical point. So some tricks are needed so that you get faster convergence. So it's an art to just these simple numbers that I'm telling you. It's not so easy to simulate on a computer, but it can be done, and people are very clever. So I think I'm done with what I wanted to tell you guys about phase transitions, etc. And now we will move on. Probably next lecture, I'm thinking of starting some other problems, and after that, we'll go to quantum gases and quantum statistical mechanics applications. Okay, there are a whole slew of beautiful applications. So I'll stop here for questions.
So for calculating beta, like from that equation we get from mu L equal to mu G.
Yeah.
There is a log 3BL minus 1.
Yeah.
So when we put it in mathematical directly, it doesn't solve. So then I put BL equal to 1 minus epsilon by 2 and expand log. So
yeah. So what you have to do is, I mean, I can show you that. That's not so hard. So you have log 3BL minus 1, right? So I said take VL to be 3 into 1 minus epsilon by 2, is it? Something like this. Right? So this is equal to log of 3 minus 1. So 2 minus 3 epsilon by 2, which you can write as log 2 plus you can do Taylor series now. You may need to go to higher order. Okay. So Mathematica will just expand it. No, you write V. So what you have to go to Mathematica or anything is to say wherever we see VL, you write this. Wherever you see VG, you write this in those equations, and then expand.
Okay, sir.
So there's no, I mean, I stopped here because expanding my hand is a pain. Right? Log of 1 minus x is x. We know that. So log of 1 plus x is x. So log of 1 minus x is minus x. So that's what I wrote there. So we can do it.